Hello, hello, hello. So you have been reading Weird Weather by Kate Evans and fact checking it to update things from 2006. And I'm going to expand a little bit on what Kate Evans has already given you a taste of in Weird Weather and update things a little bit here in this conversation. So just a reminder of what your homework ought to look like. It should be a handwritten version of something like this, where you pick facts, like this first one here. We have artificially increased the amount of CO2 in the air by 1/3, a fact from 2006 at the time that the book was written. And then you go and you fact check it, update it, give us what the new fact is. So, for example, according to NASA, it's not 1/3, which is about 33%, it's rather 50% now in just a short span of time from 2006 until today that we have seen the CO2 increase. So go through one by one, pick your 5 facts, give me the page number, and fact check them with a good source like NASA, like NOAA, the National Oceanic and Atmospheric Administration, like the United Nations, the World Health Organization, the Environmental Protection Agency, the World Meteorological Association, the IPCC, the International Panel on Climate Change, one of these reputed scientific organizations that has very solid facts, and use those. Give me the source from where you got it, something a little bit more than what I'm giving you here with a just a nasa.gov. Give me an entire citation so that I can go and find the same thing myself and double check your work. All right, so as critical thinkers, what do we always ask first as we read a book or listen to a podcast or watch a film or anything like that? Who is this that I am reading or listening to or being taught by? Who is this person, and what should I make of their potential credentials? So, Weird Weather was written by a British cartoonist named Kate Evans. So where do we put Kate Evans as a cartoonist on our hierarchy of expertise? And the answer is she's not a climate scientist by any means, right? So we shouldn't think of this book as being written by a climate scientist herself. But as you'll note in reading the book, what Kate Evans does have expertise in is taking scientific information and conveying it as a cartoonist would in ways that are entertaining, compelling, and ingratiating, so that you're able to come into the story in a way that scientists can't really tell it. So yes, she's not a scientist, but she is using science to tell the story that she wants to tell of climate change. And what she also does is give you a huge set of references. She documents every single fact that she gives in the book in great detail, so you're able to fact check her and get a sense of whether or not what she's telling you is accurate or not. So she's not an expert in the science, but she is an expert in conveying things in ways that people can take in and understand. And you can fact check all of the numbers that she gives you with scientists. So overall, for an introductory course, I think it's actually a very useful way to talk about something that is so key to what we're doing in this class, which is 2 things: learning about humans as a global system, global citizenship, and learning to think critically about the information that we come upon in the world. So both of those things are well featured in this book on climate change, which is the most important thing that humans are together as a group facing right now. And this is a book that both makes it accessible and also makes it fact checkable in the way that we're doing for our homework. So that's why I think it's a really good source for us for this class. Love to hear your thoughts on that. All right, the basics. What is the greenhouse effect? What is it that we are even talking about in terms of climate change? One thing that's really important for you to be able to do at the end of this unit when you take the exam is differentiate between various terms that are potentially right now all mixed up in your head together. So, what are fossil fuels? What are greenhouse gases? What is the greenhouse effect? What is climate change? And what is global warming? These are all different terms. They're interrelated, but they're not the same. You need to be able to differentiate those terms and use them accurately and differently by the end of this unit. So make sure that you are focused on learning these terms and figuring out what's quite a little bit different about each of them. So let's start with the greenhouse effect. Okay, so our planet, as you may have heard, is a very special one. If you look at our solar system and all of the planets that are anywhere nearby us that we're familiar with as humans, none of them are able to sustain life. Our planet has this very special atmosphere that blankets it and keeps it both warm enough, but not too warm. So we are a Goldilocks kind of planet that is creating temperatures that enable life to grow and flourish within a very narrow range of potential temperatures. Our moon, which is right next to us, is in the same distance, more or less, from the sun, cannot sustain life. Mars also, and Venus, Mars is too cold, Venus is too hot. There's all of these planets around us that are entirely inhospitable to the special conditions that life needs to be able to catalyze, that is, to be able to chemically start to change and grow and produce this biome that we have on our planet. So that's the first thing to know, is that it's actually very hard to get the right circumstances for life to grow. And those circumstances on our planet are enabled by the atmosphere that surrounds us, which is neither too thick nor too thin. It is just right to be able to allow in the sun's visible rays, the visible light from the sun, and then to hold in much of the infrared light in the form of heat that is produced by those rays when they interact with our planet. And it allows some of those infrared rays to radiate back into space, but it keeps many of them in and therefore keeps the temperature not too cold on our planet. The problem is that our atmosphere is made up of a variety of gases, some of which do not interact at all with infrared rays that would emanate back off of the planet after it's absorbed in the rays from the sun, the visible light from the sun. Some of them don't interact. Those are things like oxygen, hydrogen. Those don't interact with infrared. But there are some gases in our atmosphere that do interact with infrared rays and absorb those rays or keep them in much better than many of the other gases. And those particular molecules that hold in more infrared light or absorb more infrared light themselves are called greenhouse gases because they trap in more heat the way that a greenhouse would outside in a garden. And those gases are, as you see here on the slide, they are carbon dioxide, CO2, methane, CH4, and nitrous dioxide, nitrous oxide, N2O. Those are the gases in our atmosphere that trap in infrared light and make our planet a little warmer. So again, carbon dioxide, methane, and nitrous oxide. There are a few others, but they exist in very small quantities, and we don't produce them in large quantities in ways that we need to worry about. The one that we need to primarily worry about today is carbon dioxide, which right now is accounting for about 82% of the gases that we need to be concerned about in our atmosphere. Methane is more potent in terms of its absorption or holding in infrared rays from the earth. But carbon dioxide is more plentiful and so does more of that work. So the primary thing that we're worried about is carbon dioxide. So why is it that today, as you're well aware from having learned this in school growing up, why is it that we have so much more carbon dioxide in particular in our atmosphere today than we did 150 years ago? And the answer to that is we went through what is called the Industrial Revolution, where we figured out that we could start to burn fossil fuels in order to both power our machines and to produce electricity for ourselves. So that discovery that we could take fossil fuels and convert them into energy and power is what has seen the change in human history in which we have started to put up massive amounts of carbon dioxide into our atmosphere in the form of burning fossil fuels. So the Industrial Revolution, the creation of combustion engines, and the creation of the ability to take coal and turn it into electricity, those are primarily the reasons why we have so much carbon dioxide in our atmosphere, so much more than we did 150, 200 years ago. So what are these fossil fuels specifically? You may have been at the beach here in Long Beach or in Orange County or someplace near here and looked out into the ocean and seen these towers that are sitting out in the ocean and wondered what those are. Those are primarily, there are few differences in what's out there in the water, but primarily what you're seeing out there are oil rigs that are in the water off the coast here in California that historically, and some of them still today, are pumping oil up into from underneath the sea up where we can use it and refine it here. That's not the only place where we're extracting oil from, but it's the one that's most visible to us here in Southern California. You'll also see lots of oil rigs around Signal Hill and Long Beach all over that are those machines that are up, pumping up and down constantly. Those are also pulling oil out from under the ground. We here in Long Beach and Signal Hill have had one of the biggest oil economies in the past. We're no longer as oil dependent as we once were, but oil is one of the biggest fossil fuels. So how is it exactly that fossil fuels are created? As I said, we're pumping oil from underneath the ground. So where does that all come from? All fossil fuels were once alive. So they once lived in the form of plants or animals or phytoplankton in the ocean, some form of life that when it died, it then sank underneath the ocean or it merged with the ground, and then as more and more things piled on top of it, it eventually got pressed down underneath the ground, and that compression and the heat of being underground actually changed those old life forms into what we now call fossil fuels in the form of oil or in the form of coal, or where we get a lot of oil and coal, you also start to get layers of methane that sit at the top of oil fields, which is another one of the greenhouse gases, as you saw. So all fossil fuels once were something that was alive, plant, animal, phytoplankton, one of those, that then got captured in the ground underneath the water or under the landmass in such a way that it was able to transform into this highly energy rich substance of either oil or coal or methane. So we have then pulled those substances out of the ground and we have converted them into power in various ways. Coal we have largely used burn it for electricity in coal-powered, um, coal-fired power plants. Those are less common here in California. They are very common around the world. However, one of the most common forms of creating electricity that then gets set out against a grid is coal. Oil, obviously, we convert into things like gasoline and diesel to fuel cars and trucks and other forms of transport. Methane and propane, which can be produced from oil substances, which we use to cook. We also use what we call natural gas. It's not natural, liquefied natural gas or liquefied petroleum. We often use to heat homes or to cook with. We use it for appliances. These are, if they're not natural, they do come from oil fields as well. So primarily we use fossil fuels for various forms of energy or heating for our homes in some states, our appliances, our vehicles, our electricity. All of these are coming from fossil fuels in many instances. But there's also one other major way in which we use oil, and that is to produce plastic. So if you look around you, maybe even look at what you're wearing, any of your synthetic fabrics that are not made out of cotton or linen or leather, those are all, synthetic fabrics are all made out of oil. Or if you look at your backpack, if it is made out of largely plastic and a synthetic nylon, something like that, that's oil. If you look at the chair that you're sitting on, if you look at the table that you're sitting on, if you look at your laptop, you'll see plastic everywhere around you. Plastic is also a major thing that we do with oil. So this is not just for energy, it's also for plastic, and plastic has become an increasing part of the oil and gas industry's production process. So that's fossil fuels: diesel, gasoline, propane, methane, coal for electricity. These are all fossil fuels. When we burn these, we put up carbon dioxide and methane into our atmosphere. But burning them are not the only ways, burning fossil fuels are not the only ways that we produce carbon that goes up into our atmosphere. We also put more carbon into the atmosphere when we transform land that formerly had forests or prairies or deserts on it. When we transform that into agricultural land or into places where humans live, if we cover it with pavement, that then puts carbon into the atmosphere by taking out the plant and animal life that was holding in carbon in the form of forests, in the form of prairies, in the form of even in the form of deserts, which we think of as not alive, but in fact they are very alive. So land use actually accounts for a lot of the carbon that humans put into the atmosphere. But coal is the next biggest source, and that is largely, again, as I said, to produce electricity around the world. So a lot of places have begun to shift away from coal as their source of electricity, but in countries particularly like China and even Germany recently rolled back their use of nuclear power plants to instead put in coal power electricity, which is just a strange decision on their part. But coal accounts for a very large part of the electricity that gets used in this world, and therefore burning coal to produce electricity is a massive part of the carbon that we put into the atmosphere. Oil, and then oil as it then is converted into other petroleum products, and then gas, which here is separate from oil like gasoline and diesel. Gas here means methane and the various forms of related products that are used for heating and for cooking. So oil here is what is used to make plastics, gasoline, diesel, jet fuels, things like that. And gas is methanes and other related products, if that makes sense. So you can see how much our use of coal, oil, and gas, and therefore how much our emissions of carbon dioxide and methane have gone up since 1880, when we really started what we would call the industrial era of human history. So it's not just electricity and coal and oil that contribute to the greenhouse gases. Methane is also a very potent greenhouse gas, and food production both takes carbon, and it also produces methane. So of the various things that contribute to our greenhouse gases in the world, food production and food consumption contributes almost a quarter of our total greenhouse gases. And within our food consumption, the thing that produces the very most in greenhouse gases is actually animal products. So that is not just meat, but also milk and dairy. So your cheeses, your yogurts, your all of your cottage cheeses. And within various animal products, 50% of the greenhouse gases within animal products come from just two things. They come from beef and they come from lamb. Primarily beef, since people eat a lot more beef than they do lamb. It's important to note that how you produce your beef and your lamb actually matter to how much greenhouse gases they contribute to the atmosphere. The way that we both raise and finish off beef in the United States is particularly contributing to greenhouse gases because we tend to finish them with corn, which they are not evolved to be able to digest well. And so that harms their digestive process, and they actually produce a lot of methane in the form of burps and farts, as she was pointing out in the book. So if we did not feed them corn, instead we fed them on the grass that they are used to evolutionarily eating, then we would have much lower carbon emissions from beef. But that's not currently what we do, because it is not what the industry is both trained to do and wants to do with beef production. So just note that within food consumption, you can make a greater difference to your carbon emissions if you just eliminate beef and lamb from your, basically red meats, from your diet. But if you want to go a step further and eliminate beef and lamb and milk and cheeses, dairy, that will make an even bigger impact. And if you go even further and go fully vegan, that makes an even bigger impact on what you are contributing in terms of greenhouse gases via your consumption. Now, we'll talk later about the fact that individual choices are insufficient to solving this problem, but just so that you know what your own food consumption is contributing to greenhouse gases. So here's a little breakdown of how this plays out. It's not just the meat itself and the way in which eating it and throwing it away, since so many people throw away so much of it, the fermentation in the gut, as I was saying, the burps and the farts of the cows. It's not just that. It's also the fact that we need to clear so much natural habitat to be able to raise the crops that animals need to eat. We also have to have fertilizers to be able to grow those crops. And fertilizers come from fossil fuels. They require quite a bit of fossil fuels to produce them. And then we also need grazing land for those animals in a way that offsets what the natural environment could be producing in terms of carbon sink by growing greener, bigger, and healthier, and what other animals could use. So it's that combination of cropland, grazing land, and then what we feed them in the end when we finish them off with corn and the fermentation that produces. All of that is what makes beef in particular, but beef and also lamb, so intensive when it comes to contributing methane and carbon dioxide to the atmosphere. So here's a quick breakdown on what dairy milk looks like in terms of its contribution versus oat milk, rice milk, both in terms of land use, in terms of greenhouse gas emissions, and in terms of fresh water use. We have less and less fresh water on the face of the planet, so that's another major thing that has to be accounted for and policy changed around. So if you can switch, if you don't mind switching to an oat milk or a soy milk or an almond milk, it makes a big difference to greenhouse gas emissions, land use, fresh water, and these are becoming more and more popular by the day, actually. Okay, so how much greenhouse gas emissions do we have in the atmosphere compared to earlier? We talked about the fact that since 1880 they've gone up, but we actually have a fairly specific number. And the Mauna Loa Observatory in Hawaii, which is a government observatory in Hawaii, has collected data on the carbon concentration in the atmosphere since 1960. And as you can see from the chart, we've seen just a constant increase since then until this chart goes up until 2024. We've seen a constant increase on the amount of carbon dioxide that is being tested and observed in the atmosphere at this one site, 50% higher than it was before humans started pumping carbon dioxide and methane into the atmosphere unnaturally. So you can put that date at 1850, you can put it at 1880. For my purposes, I usually put it at about 1850 when humans started to really use coal in a serious way and to start to pump out greenhouse gases. But this chart has it since 1900. What's so fascinating is to see how much carbon emissions drop when something big happens. So for example, the global financial crisis of 2007, we saw this massive dropping in CO2 emissions. Or at the end of World War II, there was a massive drop in CO2. And during the pandemic, there was the biggest drop that we have seen since we started charting this. So the pandemic, when everybody stayed home and nobody went out, just saw around the world this huge drop in carbon emissions. So it is obviously that is not what we want the world to look like. We don't want people in a lockdown, but just noticing what happens to carbon emissions when humans are still is really fascinating. So, okay, we know that we've seen this constant increase in greenhouse gases, carbon and methane in particular, since 1850 in the atmosphere. We have about 50% more carbon today than we had then in the atmosphere. So what all has this done? What does this mean? Why is this important? Why do we even care? Here is why we care. Because since the time that we started pumping out more greenhouse gases and then increasing that amount of greenhouse gases exponentially over time, you'll see a commensurate rise in our global temperatures. So this is temperatures around the world in all 12 months starting from 1850. This is average global temperature starting in 1851 and going all the way down to 2020. And you can see that although there's some anomalous years here and there where there's some hot months, like 1878 had some strong, strange heat waves. Those anomalies are really not as noticeable as this overall increasing trend towards hotter and hotter average temperatures every single year, every single month. So from 1851 to 2020, we have just seen massive differences in average global temperatures around the entire world. So here's that in another form. I like that month by month, 1851 onwards chart from the last slide. But here this is with both an annual mean and then an average that smooths things out with a 5-year range. So you get a smoother line with the 5-year smoothing. So from 1880 until 2020, we have seen temperatures around the globe increase exponentially, so that we are much, much higher than we were today. And you can see that we are now in the range. We've gotten up to about 1.2. We're actually slightly over now, 1.2. This is, if you'll note, Celsius and not Fahrenheit. And this is important because Celsius is the way in which the world as a whole measures temperatures. So note that Fahrenheit temperatures are a little bit bigger than Celsius temperatures, so that these are, if you put this into Fahrenheit, it's a little bit higher of a change than it is in Celsius. But all of the numbers that we have heard about from the scientists who are predicting what the climate will do in relationship to our temperatures, all of the numbers we've heard are in the range of 1.5 to 2 degrees Celsius as the cap at which we can increase our temperatures without hitting what are called tipping points that we'll talk about in the next set of slides, and that's in the next chapter. So we are already right at the very top of what we can get to in terms of annual mean global temperatures. So first of all, just a reminder, how did we get there? Why did it get so hot? We got so hot because we pumped so much carbon dioxide and methane into the atmosphere that we've kept in more and more of the Earth's warmth and not allowed it to dissipate out into space. So that greenhouse gas effect. So the more carbon that we have in the atmosphere, the more methane that we have in the atmosphere, the more heat that we trap, and then our temperatures that get hotter inside that atmosphere. So as that happens, then we get this average global increase in temperature that is called global warming. So if we take this as a direction, fossil fuels, they get burned, produce greenhouse gases. Greenhouse gases, carbon dioxide and methane in the atmosphere, produce global warming. So then the question next is, what are the effects of global warming? As the temperatures get higher and higher and higher around the world, year after year, what are the effects? The effects are many, and that's again because our planet is such a special and carefully calibrated place for sustaining life. And life is very delicate. So all of the processes that enable life to form here don't have a lot of wiggle room, and they're very sensitive to changes in temperature. But and then they reverberate onto each other. They start impacting and affecting each other as well. So here are a few quick rundown of some of the effects that global warming has on the planet. Global warming overall increases heat waves. So you'd think, of course, higher temperatures, that's a heat wave. It's not actually. Higher temperatures are just higher temperatures. But a heat wave is a specific era of really high heat that is not able to go back down and that lasts for a short period of time. So with increase in global temperatures, we also see a lot more heat waves. Overall, those higher temperatures are melting the massive ice caps that sit at either end of the planet. North Pole and the South Pole both have huge amounts of ice at them, at their poles. And as the temperatures rise, then we are seeing those ice caps start to melt, and that melting ice flowing into the ocean and increasing our ocean levels. We're also seeing oceans acidify, which I'll explain in a minute. We're seeing ocean and forest life die. We're seeing the tundra and the permafrost, which is different than the polar ice caps, melt. And we'll talk about that in terms of tipping points in the next chapter. We're seeing a higher increase in massive storms, including hurricanes and also including tornadoes. We see those increase both in their frequency and in their size. So they're happening more often and they're bigger. We're also seeing polar vortexes circulate further. So the North Pole has a certain ring that keeps in really cold temperatures right at the pole, but with the changing climate, those cold temperatures that sit at the pole are actually getting pushed down further into Canada and into the northeast of the United States. So we're getting cold snaps and really extreme cold snaps that are coming with polar vortexes on a more regular basis. And we're seeing glaciers at the top of mountains completely melt and not get returned to their original level. And we're seeing more and more snowpack melt so that we're not able to keep the snowpack that we are used to relying on for our water sources in summer months anymore. And that is contributing to, but it's not the only contributing factor, of increased droughts. So increased heat, increased droughts, and all of the problems that come along with those increased droughts. So let me go into some of those in greater detail. First of all, note that the effects of global warming are not equally distributed around the planet. The North Pole is heating up at a much faster rate than the rest of the planet. So the melting that's going on up there and the death to the boreal forests that are up near the ice caps, the Arctic Circle, that is happening at a much faster rate than changes anywhere else on the planet. It's an important thing to note. This is not equally distributed. Here in the United States, we have seen our heat wave frequency, our heat wave duration, the length of our heat wave season, and our heat wave intensity really, again, not fully exponential, but in terms of the length of the season and the frequency of having the heat waves, we're seeing exponential growth in heat waves around the country. In Europe, a really massive heat wave hit in 2003 that was so intense and so unusual that really no one was prepared for it. And as a result, 39,000 Europeans died in 2003 from this heat wave that no one was anticipating. Most of those people were elderly. A lot of steps have been taken in Europe to bring in air conditioning and other systems that would help to offset future heat waves, which have continued. But just to note that how costly these heat waves can be in terms of human life. So 2023 was a huge jump up in terms of heat, and 2024 has been something similar. We're on track for 2025 and onwards to also surprise scientists with the unprecedented levels of heat and unanticipated levels of heat. So here is a picture from July 2023, which was, at the time, it's been surpassed since then, but at the time, the hottest month on record. You can see that certain places are much hotter than others, and again, a lot of that is up in Canada, closer to the North Pole. And the heat patches which can travel around with the atmosphere. The heat patches are concentrating in different areas and impacting different areas in different months. But you can see it's really concentrated here in the Middle East and Southern Europe, also in the east of Canada, and in the north of Canada as well. And so this is, you can see just how intense some of the heat can get in certain places around the world. In that same month, July 2023, the US issued excessive heat and humidity warnings. Mexico saw hundreds of people die with temperatures that exceeded 40 degrees Celsius. The UK saw its hottest ever temperature of 15.8 degrees Celsius. Spain saw a temperature that rose to 44 degrees Celsius, which is just incredibly high for Europe. Pakistan, there were dozens of people who died of heat stroke. In India, well over 100 people died of heat stroke. And in China, there were over 40 degrees Celsius temperatures, which were record-breaking heat in China. So this is a global phenomenon of this incredibly intense month of heat. And in 2024, some of you may remember the reporting on this. Phoenix, the hottest city in the United States, the hottest large city in the United States, it hit its own record. It saw 100 straight days of 100 degrees of temperatures. 100 days of 100 degrees, which had never happened in Phoenix before. When you think about heat, oftentimes we think about, well, you know, I mean, it's not too bad. I just stay inside where the air conditioning is, which is fine. But for 100 days straight, the thought about like not being able to go out and walk your dog because the asphalt is too hot, or your kids not being able to go outside and play because the sidewalks and the monkey bars and the swings are too hot, or you're having difficulty going to the grocery store because like everything outside is so hot. Like this, as this builds over time, it's not something that you can address with just little bubbles of coolness. It gets much more complicated, particularly for all of our outdoor infrastructure that's not built to endure these many days of this much heat without any reprieve. So as the polar ice caps melt, the average ocean level rises, and that hits slightly differently in different places, but all of our low-lying island nations are at risk and are currently fighting the impacts of ocean level rise, which has not only eaten away their beaches, but it's continuing to creep inland and actually to submerge their cities and their towns, so that in short order we will see countries like, and these are not all, I'm just telling you some of them, the Solomon Islands, Kiribati, Marshall Islands, Tuvalu, and the Maldives. All of them will be underwater. So these are entire languages, these are entire cultures, these are entire nations who, for no fault of their own, because they haven't really contributed much in the way of carbon dioxide to the atmosphere or methane to the atmosphere, they've contributed almost nothing. They are going to lose their nations, lose their land, lose their people's place of origin as a result of climate change. So sea level rises won't just impact low-lying nations that are islands, but they'll also hit cities around the globe. And some cities are really at a great deal of risk of the rise of the sea level. And in the United States, some cities like Miami, for example, are already really struggling with increased levels of seawater, because they are built on really porous rocks, and the sea just comes right up through the foundations on which the city is already built, and there's really nothing you can do about the rising levels of the ocean, which are coming up underneath the city and flooding it on a regular basis. So you can see some of the cities that are particularly vulnerable to sea level rise. And sea level rise means not just that the beach is getting eaten away and that people who live on the coast are having their houses submerged. It also makes you vulnerable to storm surge because the sea levels are higher. So when there's a big storm, you get a lot more storm surge. So sea level rise has a variety of problems associated with it. So here in Long Beach, where we live, we have seen a massive increase in coastal floods, which we get on a regular basis in relationship largely to storm surge from sea level rise. You can see the increase decade over decade. And here in Long Beach, the areas that going forward in the future are particularly vulnerable to increased sea level rise. You can see that all of 2nd Street in Long Beach and Naples Island and much of Belmont Shore, much of Seal Beach and around the port and the areas that are built. So all of the areas that are port areas that are now holding a lot of containers, so one of our major forms of business in Long Beach, are at risk of being underwater. So you can see that it's in Long Beach, it's not just Belmont Heights, but it's also into Alamedas Heights, and that gets us right into the bottom of Long Beach State. We call ourselves the beach, and based on these estimates, we will literally be the beach in not that many years with sea level rise. So one thing that happens with climate change and increased carbon dioxide in the atmosphere is not just that the ocean levels rise, but that the ocean becomes more acidic as well. And that's because we have more carbon dioxide in the atmosphere. Think about a fizzy drink that you drink, like a soda or a pop, like a Coke, for example. What makes that fizz is carbon dioxide, right, in your drink. So with more carbon dioxide in the atmosphere, the carbon dioxide actually interacts with the ocean water and pulls in the carbon dioxide out of the air and makes for more carbon, more fizz in the ocean itself. And as it starts to acidify and get more carbon into it, it becomes more and more difficult for sea life to make calcium-based shells, because calcium is super basic, and the acids from carbon dioxide actually eat away at the calcium-based shells and make it difficult for them to form in the first place. So ocean life that uses shells in any form finds a more difficult path towards creating life. So shell-based life in the ocean is getting more deformed through ocean acidification. We're going to talk about this more in relationship to tipping points in the next chapter, but note that the harm to the ocean is not just in rising levels of water, but warmer water damages the sea life, makes it difficult for it to grow and to prosper. Because again, life needs a very narrow range of temperatures for it to reproduce itself and to live and thrive. So warmer ocean levels actually kill off ocean life, and more acidic ocean levels actually kill off shell-based ocean life as well. Similarly to the oceans that get heat stressed, our forests get heat stressed as well. And when our forests are heat stressed, they not only become drier and they become easier to burn, but they also become more susceptible to pests, bugs and beetles and things that bore into them. They're not able to push those away as easily. They don't have the same defense mechanisms available to them. So as the temperatures have risen, we have seen across the United States and Canada, we have seen forests not only get heat stress, but they also are getting pine beetle and other kinds of beetles boring into them and killing the trees. So for over a decade now, we have had a massive problem with dying forests from pine beetle and from heat-stressed trees that have then been the not only have we seen the decrease in forest life and the decreased ability for the trees to pull carbon out of the atmosphere, which is I'm going to explain it in a second with the carbon sink, but also then become dry enough to become the kindling for fires. So heat-stressed forests are a problem in a variety of ways for the ecosystem and for the atmosphere. So one of the other major things that we see change as global warming continues to increase is, as I mentioned earlier, increased storms and hurricanes. So this has been a problem watching these increase around the world for some time. And I'm going to give you a few examples of them. These are things we've been very familiar with in our own news cycles here in the United States recently. But in 2009, for example, in the Philippines, 464 people lost their lives in what's called Typhoon Vamco. And there was $750 million of damage in that country, 2009. In 2022 in Pakistan, one third of the entire country was flooded underwater. So much so that people were forced to evacuate to just a tiny little strip of land, and all of the crops that had been planted that year were underwater, and so there was no food from their own crops. So 33 million people in Pakistan were really severely affected by this flooding, and 1,500 people, more than that, died because of this massive set of storms that hit the country and dumped water and flooded the entire country. Well, 1/3 of the country out. So imagine 1/3 of the United States, just for proportions of what that would look like, what that would be like, 1/3 of the United States being suddenly underwater. That was 2022. In 2024, you may remember Nigeria experienced similar levels of flooding, in part because the storm that hit broke one of their dams, kind of similar to Katrina that we've been learning about in this class, and submerged an entire area that was underneath that dam. It's probably time to rethink big dams and their what they have to offer us as humans. I think the era of big dams are probably over. And in 2024, September of 2024, there were massive unexpected floods in Central Europe as well. So Germany, Poland, Slovakia, Austria, the Czech Republic. People were there, as you can see from these photos, there were rapid rivers that flowed through, flash floods, and massive damage done to many countries, many people losing their lives as well. Similar time frame in Spain, so at the other end of Europe, there were huge floods, and 232 people died in 2024 from floods in Spain. These are experiences that we are very familiar with here in the United States as well. We had in 2024 a whole season of massive hurricanes that just devastated a massive swath of our country in the southeast, and we saw 372 people dying. There were billions and billions and billions of dollars of damage done by these hurricanes, and there's absolutely no we're nowhere near being able to rebuild. But so if you didn't know about these hurricanes and these floods in the United States and in Europe and in Nigeria and in Pakistan, I would suggest to you that you aren't following the news closely enough. I know that it's not a good idea to follow it too closely, but you do want to know what's happening in the world. So if you didn't know that we had a large part of our country devastated by massive hurricanes in 2024, think about where you're getting your information from and the fact that you're not getting enough news, and make sure and add in a news check once in a while and be up to date on what's going on in the world. So in 2025, we've had massive tornadoes that have killed 35 lives. And in 2025, there's one thing that I'm sure everyone remembers. We've had huge fires here in Los Angeles that killed 29 people, devastated entire communities, and saw billions and billions and billions of dollars of damage done. So I hope that you or your family did not experience this, or that you don't know someone who did, but I suspect that many of you were impacted. So yours is one of the tragedies that is related to a whole host of other tragedies around the world that are fueled by climate change, greater intensity and greater frequency of fires and floods and tornadoes and hurricanes and droughts, all of this. So I just want to show you some of the economic fallout that we are experiencing in the United States as a result of climate change. So Verisk is a company that creates data analytics for the insurance industry, and they have put together their own stats on what's happened to insurance claims just in the last year. And as you can see, insurance claims have risen significantly in the United States, and the costs are going up as well as the number of claims. So the total cost of the claims is rising rapidly from 2010 until 2024, which are the data that we have available so far. And they break that down by various kinds of claims. And as you can see, water, wind, hail, a combination of those, and then fire are the greatest reasons why people are making more and more claims, and those have really increased recently. So what this does, as you can probably guess, is not just impact those people who themselves experience the fire or experience the flood or experience the hurricane. Instead, it increases all of our costs, not just because the government comes in to clean up and to give disaster relief, which then costs all of us taxpayer money, and then there's all of the money the government needs to pay to replace the infrastructure that got damaged. So there's all of those costs to us, but also as the insurance industry continues to try and cope with the costs of these natural disasters, all of us are getting our insurance rates skyrocketing. Many people are not even able to buy insurance for their homes anymore. So there's a whole set of economic costs to this for us individually and collectively. Okay, so what I want you to be able to do for the exam is I want you to be able to tell me what fossil fuels are, where they come from, what they are, what are their names, what are greenhouse gases, how are they produced, what do they do, what is global warming, what does global warming cause, how does it how does climate change come out of global warming? What are the primary effects of climate change, and what are the costs of climate change? So if there's aspects to this that you feel like you're not really certain of from reading the book or from listening to this video, please hit me up and ask me more questions. I'm very happy to explain more things to you if some of it's not quite clear. I'll also put up some videos. But the most important thing that I want you to know and be able to speak speak to in a way that is articulate is the fact that climate change is not some future experience. It's not something we are trying to save ourselves from in the future. Climate change is happening now. We have seen massive increases in temperatures, so global warming, and with those massive increases of global temperatures, we are seeing huge increases in natural disasters like fires and droughts and floods and hurricanes and tornadoes and etc. All of that. So we are experiencing that now, and it can continue to worsen in the future and likely will in the near future. And it's not that we are trying to save our children from experiencing climate change. It's that we are already experiencing it, and we need to save ourselves now from climate change. So just want to make that quite clear. But go through this list of questions, and if there are aspects you don't understand, please reach out to me. Happy to answer more in more detail.